St. Joseph's College for Women Autonomous, Visakhapatnam, Department of Mathematics welcomes you for the online course on Real Analysis, Module 1, Real Numbers and Real Sequences. My name is Dr. V. Gauri Shankar Rao, MSc MPhil PhD, Assistant Professor, Department of Mathematics, St. Joseph's College for Women. Let us see this. One more important definition, neighborhood. What is the meaning of neighborhood? In this section, neighborhood means they can denote a shortcut NBD. NBD means it is a neighborhood. Neighborhood means it is a near value. For example, epsilon is there. Epsilon value is the 1. So what is the nearest value? Epsilon 1, 0.8 and 1.2. Why? Because of I can take that value is the 0.2. So I can remove that 1 minus 0.2, that value is the 0.8. So it is a neighborhood of 1. At the same time you can add the 1 plus 0.2 is the 1.2, and this one also neighborhood value. So here 0.8, 1.2 is the neighborhood values of 1. So neighborhood means the simply you can remember that it is a nearest value. So that is a major important point of on this neighborhood section. So epsilon distance, it is a real numbers. Some real numbers are near to epsilon. In that time you can take sometimes, for example, epsilon equal to 1. So you can take the 0.1. What is the neighborhood values? 0.9 and 1.1. So like this you can mention the neighborhood values on this. So let us see this limit point of a sequence. Here what is the limit point of a sequence? A real number L is said to be limit point of a sequence. Limit point of a sequence Sn if every neighborhood of L contains infinite number of terms of the sequence. So limit point of a sequence means what is it? A real number L is said to be a limit point of sequence Sn if every neighborhood of L contains infinite number of terms of the sequence. So near values, for example, L is a finite number. So how we can say it is that here near the so many limit point of sequence number of terms is there in sequence. For example, note a real number L is a limit point of a sequence Sn. A real number L is a limit point of a sequence Sn implies given epsilon greater than 0, Sn belongs to 1 minus epsilon L minus epsilon comma L plus epsilon for infinitely many values of n. So for example, L value is a 1, you can remove that epsilon value. At the same time you can add the epsilon value. So automatically these are the numbers of infinitely many values. You can assume of L value the so many. In that time you have to take many values of n. So that is modulus S minus L less than epsilon for infinitely many values of n. The second note, limit point of a sequence is different from limit of a sequence. Limit point of a sequence is different from limit of a sequence. If L belongs to R is the limit point of a sequence Sn, then for epsilon greater than 0 there exists m belongs to n such that modulus Sn minus L less than epsilon for all n greater than or equal to m. Thus every neighborhood of L contains all except a finite number of terms of the sequence. Whereas if L belongs to R is a limit point of the sequence Sn, then every neighborhood of containing infinitely many terms of the sequence, does not exclude the possibility of an infinite number of terms of the sequence lying outside the neighborhood. So let us observe this here, the two simple points. For example, how we can say the neighborhood? For example, L is the 1, you can remove the 0.2. So 0.8 is the neighborhood. At the same time 1 plus 0.2 and 1.2 also neighborhood. How we can say these values? Modulus Sn minus L less than epsilon. Here you can remember that minus epsilon and epsilon near to epsilon values is called as a neighborhood. Here you can take that so many values. That is the first point. The second, the limit point epsilon greater than 0. What is the convergence? Epsilon greater than 0, there exists m belongs to n such that modulus Sn minus L less than epsilon. In this case also you can find the every neighborhood of L contains all except a finite number of terms of the sequence. For example, L is the 2. So except 2, you can take that each and every term is called as a neighborhood point. Whereas if L belongs to R is a limit point of the sequence Sn, then every neighborhood of containing infinitely many terms. For example, you can take that L is the finite 2. You can take that the many neighborhood points infinitely. So that's why they can say it as infinitely many terms of the sequence. Many terms of the sequence does not exclude the possibility of an infinite number of terms of the sequence lying outside the neighborhood. Let us see the third point. So what is the third point? Limit of a sequence is a limit of the sequence, but a limit of a sequence need not to be the limit of the sequence. So limit of a sequence is a limit point, but sequence limit point of a sequence need not be the limit of the sequence. So that point is a limit, but it is not a sequence. For example, 2 is there, that point is a limit point 2, but it is not a sequence. So limit point is also known as cluster point. So limit point, one more name is called as cluster point or condensation point or accumulation point or subsequential limit. Here how we can say limit point is also known as cluster point or condensation point or accumulation point or subsequential limit. So these are the names. For example, note limit 1 plus 1 by 2n power of n equal to limit 1 plus 1 by 2n power of 2n power of 1 by 2. So this value they can treat it as e. Remember this. Limit n tends to infinite 1 plus 1 by 2n power of 2n they can treat it as e. Power of 1 by 2 can written as 1 by 2. 1 by 2 means can I write root 2. It is a root e. So let us see this second. Limit 1 plus 1 by n square 2n square is there. So can I write a power of m into power of n? How we can write a power of m n? So this 2n square written as a power of m power of n. So that's why it can be written as n square power of 2. So this value they can treat as like e. So this is e square. Here you can observe this. So this value is root e and this value is the e square. So let us see this one theorem. If L is a limit point of the range of a sequence Sn, L is the limit point of the range of a sequence Sn, then L is a limit point of the sequence Sn. Here you can observe this as the simple technique. L is a limit point of the range of a sequence. Then L is a limit point. This is a L limit point. Here what they can say? Limit point of the range of the sequence. What is the total range? Here L is a limit point. Let us see this. Let S equal to range of the sequence Sn. Our assume S is the what is that? Range. L means what is that? Limit. L is a limit point of S. Here S is a some range. For example 1, 2, 3, 4 is there. So on. It is a range. So in that values, for example, I can take 2. 2 is called L. L is a limit point of S. Every neighborhood of the L contains infinite number of terms of the set S. Every neighborhood of the L contains infinite number of terms of the sets. So L is the 2. You have that. So there's so many numbers is there in that set. But each element of the set S is a term of the sequence Sn. Each element, what you can consider that each and every element compulsory it should be as like sequence Sn, the related sequence. Every neighborhood of the L containing infinite number of terms of the sequence Sn. Therefore, L is a limit point of the sequence Sn. Here, for example, you can take the 2. 2 nearest values, how many? The so many is there. So, each and every value should be containing Sn sequence. So, therefore, L is a limit point of the sequence Sn. So, let us see this small theorem. Prove that every bounded sequence has at least one limit point. Every bounded sequence has at least one limit point. Actually, bounded means what is that? You have the lower value, at the same time upper value existed, but they can say at least one limit point. You can prove as at least one limit point. Let us see this. Sn be the bounded sequence. Sn be the bounded sequence. Let T be its range set. Sn is a bounded sequence. For example, -1 Sn less than 1 is there, minus 1 to 1. In that time, how we can say the range is minus 1 and 1, like T be its range set. T is bounded, capital T is bounded. So let us see this case 1. T is bounded means if capital T be a finite set, capital T be a finite set, capital T equal to A1, A2, AN. Already they said na, capital T means what is that range? What is the range of these elements? A1, A2, AN. Let Ni equal to, set n belongs to capital Ni for all such that Sn equal to Ai for 1 less than or equal to I less than or equal to M. So the simple thing is I varies from 1 to M. Here you can take that n belongs to capital N1. Here you can put n equal to some small n. This is a natural numbers related. That is the first value. Otherwise you can treat it as like Sn. Sn means what is that? A1. For example, here you can put I equal to 1. So Sn is equal to A1. A1 is the first element of the given set. So at the same time, union Ni equal to n. If n1, n2, so on nm are all finite, then Ni equal to n is finite, which is not true. At least one Ni is an infinite set for I equal to 1 to so on m. Here you can observe that T is the range. So this range set, range means what is that? That all elements should be involved in that capital T. So these all elements should be related to Sn. So once Sn is the bounded values is there, at the same time lower boundary values is there, at the same time upper boundary values is there. So that lower and bounded values already it is involved in the finite set. This finite set is called as range set. So this is like, you look like you can write, for example, S1 is there, A1 is the first element of the Sn sequence, like. So these all elements they can treat it as capital N1, capital N2, capital N3. So these all elements when you can take that capital N. So that's why you can write as these all union elements it can be written as capital N. So these all are the finite. So therefore, which is not true, at least one is a finite. Why? Because of, you can say it is a one limit point. So here the so many limit points is existed, but you can say one limit point is existed. So at least one Ni is an infinite set for I equal to 1 to so on M. Let it be Nk. So you can say one limit point is existed. So let it be Nk. So Sn equal to Ak. Ak means what is the last term of that? For infinitely many n belongs to capital N, so therefore Ak is a limit point of Sn. Here Sn is the one set of numbers. So in that set of numbers they can introduce Ak is the one limit point. So what is the case 2? If 2 is an infinite set, 2 is an infinite set, T is bounded by Bolzano-Weierstrass theorem on aggregates capital T has a limit point say L. So therefore L is a limit point of a sequence Sn. Before you can take that range. In that range you can say one Ak value is the only limit point of the Sn. But case 2 how they can say it? If T is an infinite set, you can take that it is an infinite set, it is not finite. So there is no end. So by the Bolzano-Weierstrass theorem it is aggregates capital T. So once it is an aggregate capital T has a limit point value is L. So once limit point L is existed, so the single limit point existed on sequence Sn. So this is the theorem. So let us see this one more theorem. Prove that the set of limit points of a bounded sequence is bounded. Set of limit points of a bounded sequence. Once it is a bounded sequence what is that? You have the lower boundary, at the same time upper boundary. Once the lower boundary and upper boundary is existed, it is a bounded. So in that time you can say Sn is a bounded. It means K1 less than or equal to Sn less than or equal to K2. K1 is the lower boundary, K2 is the upper boundary. In that time Sn is existed. So Sn treated as like bounded. Let us see the proof. Let Sn be a bounded sequence. Sn be a bounded sequence. Once Sn is a bounded, what the values is existed? There exist K1, K2 belongs to R such that condition K1 less than Sn less than K2. K1 is the least value, K2 is the highest value. Sn is bounded. This is a condition of bounded. So what he can prove? The limit points of a bounded sequence is bounded. The set of limit points. Let us see this. We can take. So therefore Sn does not belongs to minus infinite comma K1. K1 means what is the lowest value now? So that lowest value it can be treated as minus infinite comma K1. So Sn does not belongs to K2 comma infinite. So here, so Sn is, it is not relevant to this value. At the same time Sn is not relevant to k2 comma infinite. So the finally L belongs to R. It is a finite. L belongs to R. So L is existed on L. What is the related? L is minus infinite to comma k1 union. So closed bracket k2 comma infinite open bracket is not a limit point of the sequence. So in between it is not a limit point of the sequence. You can observe this minus infinite comma k1 union k2 comma infinite closed bracket k2 comma infinite is not a limit point of the sequence. L belongs to R and L belongs to k1 k2 is a limit point of the sequence. Here simply you can say k1 is a limit point. So k2 is a limit point. You can observe this is a increasing sequence and this is a decreasing sequence. Once you can take individual increasing or decreasing sequence, once you can take decreasing sequence, k1 is a limit point. For example, here the k2 is the limit point of a sequence. It is existed on only k1 k2 but not a minus infinite to k1 and k2 to infinite. So these values, many values is the limit point of sequence, but here the clearly existed on only k1 and k2. So therefore limit point of the sequences, the set of limit points Sn is bounded. So you can see this one more theorem. Prove that every bounded sequence has the greatest and the least limit points. What the theorem is? Prove that every bounded sequence has the greatest. Bounded sequence has the greatest and the least limit points. So what you can prove? Bounded sequence has the greatest, at the same time least limit points. That limit points is called as a least. So let us see this proof. So what they can say, Sn is the bounded sequence. Now we prove that the sequence Sn has the greatest and the least limit points. You are proving like Sn is the greatest and you can say the limit points are the least. So the condition Sn is the bounded implies Sn has at least one limit point. So Sn means it is a bounded. Bounded means you have the lower and upper. But here we can say it is a at least one limit point is existed. So already the two limit points existed, but you can say it is a at least one limit point existed. Let the set of limit points of the sequence Sn is 0. Our assumption, set of the limit points of the sequence Sn is 0. Since Sn is a bounded, S is the set of limit points of Sn. S is the set of limit points of the Sn. So S is bounded and non-empty. Once S is a bounded, you have the two values existed. One is the lower value, the second one is the upper value. So automatically the values is involved. How we can say it is the, so that's why they can say it is the non-empty. By completeness axiom, S has infimum and supremum. The lower value is there, at the same time upper values is there. The limit points means you have the so many neighborhood points is involved. So that's why automatically S they can read as infimum and supremum. So let us infimum S equal to small u and supremum S equal to V. Now we prove that u comma V belongs to S. So these two elements should be S. So let epsilon greater than 0, supremum S equal to V, there exists some x belongs to S such that V minus epsilon less than x less than or equal to V plus epsilon. Here you can observe this, that simply you can minus epsilon and plus epsilon. At the same time you can treat as like one lower value, at the same time one upper value. So for example, x treated as like sequence, x before value is a V minus epsilon, x after value is a V plus epsilon. Why? Because of you are talking about bounded. Bounded means you have the two terms is involved. One is a lower and the second one is a upper. So that's why you can write. So convergence, you can take the convergence. Once the convergence is involved, automatically you have that one value left side, the second value is the right side. Once right value is the big one and the left side value is the small one. So automatically bounded sequence is existed. Then implies x belongs to V minus epsilon, V plus epsilon. So these are the two numbers. So these are the neighborhood of x. For example, we can take it as like some 3. You can remove that epsilon 0.5. Automatically this value is the 2.5. You can add the epsilon 3.5. 2.5 and 3.5 is the neighborhood points of the 3. 3 is the L value. So it is a neighborhood of X. So therefore X is a limit point of sequence Sn, implies every neighborhood of X contains infinite number of terms of Sn. So limit point of X is a limit point of Sn, implies every neighborhood of X contains infinite number of terms of Sn. So simple I was given as 2.5 and like 3.5. Not only 0.5, you can take 0.3, 0.2, whatever it is. There's so many values you can remove and addition. So automatically you have that infinite number of terms is involved in sequence Sn. Each and every term is involved in Sn. So v minus epsilon comma v plus epsilon contains infinitely number of terms of the sequence Sn. Every neighborhood of v contains infinite number of terms of Sn. So v is a limit point of Sn. So limit point of Sn, v is a limit point of Sn. You can remove that any values, epsilon replace with 0.5, 0.3, 0.2, whatever it is. So automatically v they can treat it as like a limit point of Sn. So once you can remove that minus epsilon plus epsilon, these are the neighborhood points. So therefore v belongs to S. The similarly u belongs to S. Every bounded sequence has the greatest and the least limit points. So once it is a bounded sequence, there is the greatest, at the same time least limit points also existed. So let us see this one more theorem. Prove that sequence is convergent if and only if it is bounded and has only one limit point. So what you can prove? Sequence is a convergent. Convergent means what is that? Modulus Sn minus L. If and only if less than epsilon. If and only if it is bounded and has only one limit point. So once it is a convergent, automatically it is a bounded. So it is already proved. But they said what is the extra one is, you can say one limit point is existed. Only one limit point. Actually bounded means have the two values. But you can say it is a only one limit. So let the sequence Sn is convergence to L. Now we can prove that Sn is bounded and has only one limit point. So first of all you can take that convergence related definition. Sn is the convergent. What you can prove? Sn is bounded. So Sn is convergence means limit Sn equal to L. So what is the conditions? Each epsilon greater than 0, there exists m belongs to capital N such that modulus Sn minus L less than epsilon for all n greater than or equal to m. Here I can apply that L on both sides. I got so minus epsilon. So how we can? So this modulus how we can write? Minus epsilon less than Sn minus L less than epsilon. After that you can take that L on both sides. You got L minus epsilon here, minus L plus L is the cancel. You got that L plus epsilon. The simply you are taking the convergence property. So this convergence property how we can say it is a bounded. Once it is a bounded, you can say one is a lower value, the second one is a upper value. So that's why you can follow this process. So lower value is the L minus epsilon, upper value is the L plus epsilon for all n greater than equal to m. So compulsory m value is a existed value in n sequence. So then L is a limit point of the sequence Sn. So let L dash be another limit point of the sequence Sn. Now we prove that L equal to L dash. The before video they can explain L equal to L dash how it is a convergence. Suppose contradiction related. Suppose L not equal to L dash. Our assumption, let epsilon equal to modulus L minus L dash by 2 greater than or equal to greater than 0. Epsilon value I can assume L minus L dash by 2. It is some particular value but it is not a 0. Since limit Sn equal to L for epsilon greater than or equal to 0 such that m belongs to n, modulus Sn minus L less than epsilon for all n greater than or equal to m is a convergence property. L dash is a limit point. So L dash limit point means what is that? Here L is a limit point means lower value is L minus epsilon, upper value is the L plus epsilon. But here we can talk about L dash. L dash is a limit point. How we can say this one also the same property involved? L dash minus epsilon comma L dash plus epsilon for infinite number of values of n. So L dash minus L epsilon is the lower value, L dash plus epsilon for the upper value for an infinite number of values of n. So this one, it can be written as, it is nothing but modulus Sn minus L dash less than epsilon. For an infinite number of values of n, for an infinite number of values of n, this convergence property, it is involved on infinite number of values. So here, so consider modulus L minus L dash equal to, so this one can I written as minus and plus n is the extra term, you can add and minus. So after that you can take the modulus as separately. So modulus means it can be written as reverse also. So Sn minus L plus Sn minus L dash. Sn minus L means what is that? Convergence property. So Sn modulus Sn minus L less than epsilon. This value is the epsilon, and this value is equal to also epsilon. Epsilon plus epsilon is the 2 epsilon. So this 2 epsilon is equal to modulus L minus L dash. So therefore modulus L minus L dash less than modulus L minus L dash. This is not yet true. Why? Because of you are taken L not equal to L dash. But the finally this is due to our supposition is the wrong. L not equal to L dash your consideration. But the final you can prove L minus L dash. It means what is that? L equal to L dash. So that's why our supposition is the wrong. So the unique limit is the existed. Conversely, suppose that sequence Sn is bounded and has only one limit point. So what is the conversely? The sequence Sn is bounded and has only one limit point is existed. Now we prove that sequence Sn is convergence to L. So once sequence Sn is convergence to L, the single limit point is existed. Simply. So what is that? Bounded means the sequence Sn is bounded and L is the only one limit point. So it can be treated as Sn belongs to L minus epsilon comma L plus epsilon. So Sn is in between existed on L minus epsilon comma L plus epsilon, except for a finite number of values of n. For a finite number of values of n. Why? Because of you can say it is a convergence. So let Sm1, Sm2, so on Smp be the finite number of terms of the Sn sequence that lies outside L minus epsilon comma L plus epsilon. Let small m equal to maximum of m1 comma m2 comma so on mp. Here you can assume that m equal to as a maximum set of m1 m2 so on mp. So therefore Sn belongs to L minus epsilon comma L plus epsilon for all n greater than or equal to m. What you can consider, the both values should be existed on left and right sides. So once you can take left and right side, the small value, big value, you can apply the modulus also. So once it is a modulus is there, it is a bounded, at the same time convergence. So therefore for any epsilon greater than 0, there exists m belongs to n such that modulus Sn minus L less than epsilon for all n greater than or equal to m. So therefore the sequence Sn convergence to L. Here you can remember that one more. The bounded sequence, the convergence sequence is the bounded. So bounded sequence, you can say that one limit point is existed. So one limit point is existed, you can separate them. Either L minus epsilon, L plus epsilon, the both values existed, it is a bounded. Once you can remove that, only you can take that one value. So that only one value existed, it is like as convergence. So that's why epsilon greater than 0, there exists m belongs to n such that modulus Sn minus n less than epsilon. So automatically the sequence Sn convergence to L. So therefore the convergence is a sequence is a bounded, but bounded sequence is not a convergent, but you can add epsilon or plus epsilon. You can pick up that one value, in that time it is the single limit point is existed. Let us see this theorem. Prove that L belongs to R is the limit point of a sequence Sn if and only if there exists a subsequence of Sn that converges to L. What the problem is given, theorem is given? Prove that L belongs to R. The finite value is real, is a limit point of a sequence Sn. Limit point of a sequence Sn if and only if Sn is a limit point of a sequence. Sn sequence limit point L. If and only if there exists a subsequence of Sn that converges to L. You can take subsequence. That subsequence also convergence. L also it is a convergence. In that time you can pick up that subsequence also, you can say it is a convergence. So for example 1, 2, 3, 4 is there, but what is the odd subsequence is 1, 3, 5. That one also you can say it is a existed. Like suppose L belongs to R is a limit point of a sequence Sn. So what you can assume? limit point of sequence Sn means L belongs to R. Now we prove that there exists subsequence of Sn the convergence to L. Subsequence also you can say it is a convergence to L. The sequence Sn convergence to L. So since L belongs to R is a limit point of a sequence, L belongs to R is a limit point of a sequence Sn. So once it is a limit point is existed, every neighborhood of L contains infinite number of terms of Sn. Once the convergence property is limit point is existed, each and every neighborhood point of also existed. For example, 1 to 50 series is there, the 14 is the existed, automatically 14, 15, 16 and each and every term after 14 each and every term should be existed. So like that, every neighborhood of L contains infinite number of terms of Sn. For each k belongs to n, we have Sn k belongs to L minus 1 by k, L plus 1 by k. So L minus 1 by k, L is a one limit point is existed, L. So in this finite value you can remove that minus 1 by k, at the same time you can add the 1 by k. So therefore it is like subsequences related. So L minus 1 by k less than Sn k less than L plus 1 by k. So you can remove that L, just simply you can take that minus L. So after that 1 by k less than Sn k minus L less than 1 by k. Here Sn is the sequence, Sn k is the subsequence. But subsequence means what is that? Each and every element should be, it is like sequence related. So then it is a lower value and this one is upper value. Can I write modulus Sn k minus L less than 1 by k? Let epsilon greater than 0. By Archimedean property, there exists m belongs to z plus such that 1 by k less than epsilon for all n greater than or equal to m. So for example, m is z plus, so automatically 1 by k also, 1 by k means on some particular value. It one epsilon is the big value comparing to 1 by k. So therefore modulus Sn k minus L less than 1 by k. So that value is less than epsilon for all n greater than or equal to m. So modulus Sn minus L less than epsilon. But here you can take the subsequences. That's why you can write less than 1 by k. 1 by k always less than epsilon. Why? Because of epsilon is the convergence related. But you are taking the subsequence. Subsequence is the 1 by k. So automatically comparing to epsilon, 1 by k value is the small. Therefore Sn is a subsequence of Sn that convergence to L. Therefore Sn is a subsequence of Sn then convergence to L. Sn is a convergence. Once you can take subsequences. Subsequence here 1 by k are denoted like that. So 1 by k related each and every value is also convergence. But this value it is particularly comparing to epsilon, it is a small one. Conversely, suppose that there exists a subsequence of Sn that converges to L. Now we prove that, for example, L is a limit point of Sn. Now we can prove that L is a limit point of Sn. Let limit Sn k equal to L given epsilon greater than 0, there exists m belongs to z plus such that modulus Sn k minus L less than epsilon. It is a convergence property. So Sn k minus L less than epsilon means how we can write? Can I minus epsilon 2? Minus epsilon less than Sn k minus L less than epsilon. Here that modulus is there. Modulus can I write as minus epsilon to plus epsilon. After that you can eliminate that L. How we can eliminate that L? Just you can take that L on. So L minus epsilon, here L minus L is a cancel. You got L plus epsilon for all k greater than or equal to m. So m is the sequence subsequence related, k is existed in between. So every neighborhood of L contains infinitely many terms of Sn k and hence the sequence Sn. So implies L is a limit point of the sequence Sn. In this theorem, L is the limit point of a sequence Sn. At the same time, the subsequence also there exists the infinitely many number of terms in that sequence. See this Bolzano-Weierstrass theorem. So Bolzano-Weierstrass theorem means prove that every bounded sequence has a convergent sequence. The simple you can remember this in this theorem proof. For example, you can take that finite sequence. So in that finite sequence you can say at least one limit point is existed. At the same time you can take that infinite. In that time also you can say one limit point is existed. So finite or infinite you can consider one limit point should be existed. That is a Bolzano-Weierstrass theorem. So see the theorem. prove that every bounded sequence, bounded means what is that lower value existed at the same time upper value is existed, has a convergent subsequences. You can say these are the convergent subsequences. Let us see this. Let the sequence Sn is the bounded. Now we prove that Sn has a convergent subsequence. Sn is a bounded, you can consider, you can prove Sn is a convergent subsequence. So convergence at the same time subsequence is a convergent, you can prove like that. By known theorem, every bounded sequence has at least one limit point. Already it is proved. Every bounded sequence has at least one limit point. At least one limit point means it is a convergence, otherwise it is not a convergent. Let the limit point is L. So since L is a limit point of the sequence, Sn implies L is a limit point of the sequence Sn implies what they existed, there is a subsequence Snk of Sn. So this set Snk you can consider as of Sn that converges to L. So therefore every bounded sequence has a convergent subsequences. Let us see this. For example, 1, 2, 3, 4, 5, 6 is there. 1, 2, 3, 4, 5, 6 is the convergence. You can pick up the even numbers. That even numbers also convergence. So sequence is the convergent, subsequence also convergent. You can remember that. So for example, all are the good people is there. 10 members is the good people. You can pick up the some people on 10. So those persons also good people. So sequence is the convergent, at the same time subsequence also convergent. So that is a main point. Peak point of sequence. A natural number small m is called a peak point of the sequence Sn if Sn less than Sm. Peak point for all n greater than m. So if Sn equal to 1 by n when n less than or equal to 5. So for example, here you can put 1 by 5, that is called as Sn. It is like some peak point of sequence. In sequence you can find out that what is a peak point. So Sn equal to minus n where n greater than 5, then 1, 2, 3, 4, 5 are 5 peak points. How many peak points is there? Here 1, 2, 3, 4, 5, n greater than 5. So in between, before 5, 1, 2, 3, 4, 5 are the peak points. But here you can observe this less than or equal to 5. 5 is the peak point. Like note, a sequence may have finite or zero or infinite number of peaks. A sequence they have finite or zero or infinite number of peaks. Let us see this theorem, monotone subsequence theorem. So what is the monotone means? Either the series is increasing or decreasing. So every sequence has monotonic subsequence. The theorem statement is every sequence has monotonic subsequence. Let Sn be any sequence, then three cases arise. The first one is Sn has no peak point. So sequence Sn has a no peak point. The second, Sn has a finite number of peak points. You have that some limited finite number of peak points. Third, Sn has an infinite number of peak points. The no peak point, finite number of peak points and infinite number of peak points. Let us see this case 1. Sn has no peak point. So 1 is not a peak point. There exists a natural number n2 greater than 1. So after 1, so after that 1, here n2 means you consider 2, 3, 4 like. So these are the peak points 2, 3, 4, but 1 is not a peak point. So such that Sn2 less than Sn greater than Sn1. Again, since n2 is not a peak point, for example n2 is not a peak point, so there exists what is the natural numbers n3 onwards. So n1 is not a peak point, n2 onwards it is a peak points. For example n2 is not a peak point, n3 onwards it is a peak point, so like that. So this continuing this process we have subsequences Snk such that Sn1 Sn2 less than Sn3 less than where n1 equal to 1. So S contains monotonically increasing subsequences Snk. Here subsequence you can say as like peak points. So these peak points is increasing. So let us see this case 2. Sequence Sn has a finite number of peaks. Finite number of peaks means what is that? Have the limited points of peaks. Let m be the largest peak point. For example, m is the largest peak points. Let n1 be a natural number. Peak means it is a highest like. So let n1 be a natural number such that n1 greater than m, then n1 is not a peak point. So n1 greater than m, then n1 is not a peak point. n1 is a natural number. n1 is existed. So that one is such that n1 greater than m, then n1 is not a peak point. There exists a natural number n2 greater than n1 such that Sn2 greater than Sn1. Again n2 is not a peak point. So let us see this. N1 existed in that time n2 onwards. So n2 is not a peak point, you can take that before 1. So like that, here n2 is a peak point, before 1 is n3 is onwards, it is not a peak point. Here n1 is a peak point, n2 onwards it is not a peak point. So this is like continuous process. Continuing this process, we have subsequences Snk such that Sn1 less than Sn2 less than Sn3 less than so on. So therefore sequence Sn contains monotonically increasing subsequences Snk. Sn is the sequences, Snk is the subsequences. These subsequences, they have the peak points. The existed point onwards, it is not a peak points. So each and everything has like increasing sequence. Peak point means what is that? The sequence value is greater than or equal to all subsequent values. So what is it? The sequence value is greater than or equal to all subsequent values. So is it greater than or equal to all subsequent values? It is called as a peak point. So let us see this case 3. Sn has an infinite number of peak points. Sn has infinite number of peak points. Let the peak points be n1, n2, n3 such that n1 less than n2 less than n3. For example, n1 is a peak point, n2 through onwards it is not a peak point, like that. So n1 is a peak point and n2 greater than n1. So n1 is a peak point, so n2 onwards it is not a peak point. So Sn2 less than Sn1. So n2 is a peak point, n3 greater than n2. n2 is a peak point but n3 is not a peak point. Sn3 less than Sn2. Continuing this process, we have subsequence Snk such that Sn1 greater than Sn2 greater than Sn3 greater than so on. So therefore Sn contains monotonically decreasing subsequence Snk. Every sequence has monotonic subsequence. Monotonic sequence means what is that? You can say increasing sequence is the increasing sequence and decreasing sequence. Increasing sequence you can consider as more peak points. You have the peak points. At the same time you can consider decreasing sequences, you have that peak points. So once peak point, what is the main theme of peak points means? The sequence value is greater than, where the sequence value is greater than or equal to all subsequent values. So this is the every sequence has monotonic subsequence. Thank you all watching this video. Thank you.